field different here than here? Than here? It's all the same. If I put a proton here, will it have a different force than a proton here? Or here? It's the same. Now, the voltage or the potential are places where we're all at this, where if we move the positive charge in this direction, does it do any work? No. No, because the field is perpendicular to the direction. So in that case, our motion would be in the y direction, our force is in the x direction, the work is 0. So every place on each of these lines has the same potential. A particle, a charged particle, moved along one of these directions would have the same potential energy. Since the field is uniform, the potential lines are equally spaced. It works out, so the voltage increases linearly as we move from here to here, doesn't it? It works out that the voltage, this distance here, is D. We let this be our reference voltage, V equals 0. Our voltage over here will be equal to E times D. So if I separate these plates twice as far apart, and they have the same charge, what happens to the voltage across the two plates? If I move them twice as far apart, does the field change? No. Field strength is the same because I haven't changed the charge. Will I have to do work to separate them? Are they attracted to each other? Yes. Yeah. So I'll have to do work to separate them. But the field strength stays the same in between them. What happens to the potential if I double the distance between the plates? It's twice as much. So if I move a charge halfway across, move an electron halfway across this plate, and I have to do 1 joule of work, how much work will it take it to move it all the way across the plate? 2 joules. If I separate them, the field strength is the same, and now I have to move 4 times as far. How many joules of work? 4 joules. I've now moved the electron across 4 times the potential. Is there anything? If I want to double the field strength inside of here, what do I do? Does it matter? Can I put them closer together? Does that change things? No. What can I change? What if I increase the charge? Yes. If I double the charge on, then I'll get twice the field strength. So it works out. Let's do a little math here. If I divide both sides by D, what do I get? Now, what are the units of E, electric field? Newtons per coulomb, right? But what do we measure potential in? Volts. And what do we normally measure distance in? Meters. It works out that 1 Newton per coulomb is the same as 1 volt per meter. We can also measure potent fields and how many volts do we increase for every meter of distance we travel. So that tells us that 1 volt must be a Newton meter per coulomb, right? So we now actually have a unit for volts, which we've been playing with in the lab. So we have a 1.5 volt battery, that's the same as 1.5 newton meters per coulomb. Now this is all true for a uniform field. And I also have to do one other thing. If I add direction, these are all magnitudes, right? The voltage is increasing as we're going in the opposite direction as the electric field. If we move in the direction of the electric field, voltage goes down. What if we have something like a point charge where the field lines are diverging? Then the magnitude of the electric field goes down. For each itsy bitsy displacement, this is true, but as the electric field changes as we go through every point in space. Because now, if we imagine a point charge, as we move through that space, the field lines are diverging. So the math ends up being a little trickier. So this is for a uniform field. If we look at a general case, what we'll say is the electric field in a direction like Ex is equal to negative dV dx. So we're going to go from there to there. The negative tells us that if we're moving in the opposite direction of the electric field, the potential is going up. And it tells us that the rate that electric field is increasing, the stronger the field. So imagine the potential around a point charge. So we're measuring our distance r from a point charge. If we plotted our potential versus our point charge, looks something like that. Oops, that's not right. With our positive charge. As we get very close to the charge, what does the potential slope do? It gets pretty steep here, doesn't it? You get a fairly large number. We said E equals the negative of dV dr. The slope up there is rather large negative number, isn't it? But as we come out to here, now it's more of a moderate number, isn't it? And as we move farther and farther from the charge, the potential gets, the slope on that potential gets less and less negative until it comes to zero. So our electric field would also be larger and getting smaller. Now it works out for a point charge. Potential decreases proportional to 1 over r. We take the derivative of 1 over r, don't we get 1 over r squared? This decreases proportional to over r squared. made a mistake, haven't I? Because the derivative that, I apologize. Because the negative of 1 over r should give you a negative r, and then you take the negative of negative, and we should get. So if we take the derivative with respect to r, of 1 over r, negative derivative, that gives us a negative of dr of r to the negative 1 equals, let's see, negative 1, that becomes a negative, negative, r to the negative 2, gives us a onto 1 over r squared. So actually I'm okay, percent. Started to panic there. All right. Have a great 3-day or extra day weekend.